expansion. How can we make use of binomial expansion for approximation? Binomial expansion can be used to approximate expressions when the second term is small. For example, if x is small, then terms involving x squared, x cubed, and higher powers become very small and may be neglected. Useful expansions, we have 1 plus x all raised power n to be 1 plus nx when x is small, absolute x is small. Also, 1 plus x raised power n is approximately 1 plus nx plus n into n minus 1 over 2 factorial times x squared, and so on, if a better approximation is required. Let's see examples explain what we're saying better. Use binomial expansion to approximate 1.02 or raised power 4. 1.02 can be rewritten as 1 plus 0.02, and so our initial question can now be expressed as a binomial 1 plus 0.02 raised to power 4, and then we can apply our binomial expansion on this to get an approximation. That's what we're saying. 1 plus x all raised to power 4 from our expansion will give us this. You can see our Pascal triangle coefficients appearing 1, 4, 6, 4, 1. We're ascending for 1 raised to power 1, 1 raised to power 2, 1 raised to power 3, 1 raised to power. For 1, we're descending 1 raised to power 4, 1 raised to power 3, 1 raised to power 2, 1 raised to power 1, 1 raised to power 0. And then for x, we are ascending x raised to power 0, x raised to power 1, x raised to power 2, x raised to power 3, x raised to power 4. Now, in this case, our x is 0.02, and so finally, the whole expansion now becomes, we represent all x with 0.02. We now have 1 plus 4 into 0.02 plus 6 into 0.02 squared plus 4 into 0.02 cubed plus 0.02 raised to power 4. By the time we do this sum, we have our approximation, which is 1.0824316. We have similar example here. Okay, let's treat this 1.03 cube root. We want to approximate this using binomial expansion. So if we rewrite this, is the same as 1.03 raised to power 1 over 3. We can write it as 1 plus 0.03 raised to power 1 over 3. This is now looking like a binomial. But then our n in this case now is no longer a positive integer. It is a rational number, 1 over 3. Right? And for rational index, we usually make use of this formula to expand. The formula for rational index is quite different from that of positive integers, which we've been doing since. So I'll skip the rest of this example and move to the section where negative index and rational index are treated. So when we do that, you can come back to this example and it will be very clear to you. So to negative and rational indices, or indices of course is the plural of index, the binomial expansion can also be extended to expressions of this form, right? Where x is less than 1. Once any number less than 1 is rational, of course, or 0. But of course, the case for 0 is any number raised by 0 is 1, so we're not concerned with that. Now, the general form for 1 plus x all raised power n is this formula, and you can spot a pattern in this formula. We have 1 plus nx, and then the next term plus n into n minus 1 over 2 factorial x squared. In this case, we have x raised to power 1, right? Yeah, n, you can see n is decreasing like factorial. N into n minus 1 over 2 factorial. Here we can see we have over 1 factorial. We can exempt all those terms because they are not significant. Then plus, we'll follow the pattern again, n into n minus 1 into n minus 2. We're increasing our factorial over 3 factorial x cubed. The next one, for instance, would be n into n minus 1 into n minus 2 into n minus 3 over 4 factorial times x raised to power 4, and so on. So you can see the pattern. This expansion continues indefinitely when n is not a positive integer. So, for example, when we have 1 plus x raised to power minus 1, n is minus 1 in this case, so all the n we're having here, we'll substitute minus 1 for them, and x remains x. So we'll have 1, then if we substitute minus 1 here, we'll have minus x, plus, if we substitute minus 1 here and minus 1 here, first of all in the bracket, minus 1 is minus 2. Minus 2 times minus 1 becomes plus 2 over 2 factorial. 2 factorial is 2. 2 over 2 is 1. So we are left with 1x squared, which is x squared. So the same thing here as well. We'll be left with minus x cubed, and we can keep going on and on. So it's the same procedure here as well. Substitute 1 over 2 for all the n. Can see we'll have 1 plus 1 over 2x, right? Substitute 1 over 2 for all the n here, we'll be left with minus 1 over 8x squared, and so on. Same thing goes here. In this case, all the n you substitute minus 1 over 2, you get this. Now take note for this negative index and rational index, the first term of the binomial must always be 1 before this formula can work, before we can apply this expansion. So example, expand up to the term in x cubed. We've seen this already here, so we don't need to treat this example. So although you can pause and look at it, that's everything that is done there is what we've already said. Next example, up to the term in x cubed. The expansion can keep going infinitely, infinitely. That's why they are specifying where the expansion should stop in examples relating to negative and rational indices, right? So all you need is your n and whatever your x is, substitute them into the formula, you get your expansion. For the nth term of an expansion, the r plus 1th term in the expansion of a plus b all raised power n is that formula I told you we are coming back to. The r plus 1th term is given by this formula, n combination r times a raised power n minus r times b raised power r. This formula is very useful when we are asked to find a particular term or the coefficient of a given term or the term independent of x. So those are the forms in which questions will come where we have to apply this nth term formula. For example, find the 4th term in the expansion of this. So using this formula, we don't need to write out the whole expansion that will have 7 terms. We can fish out that 4th term with this formula. If we are looking for the 4th term, it means our r will be 3, right? So that the term will be t4, standing for 4th term. So once we know r is 3, substitute it in here. We already know that n is 6, right? So 6 combination 3, and then a raised to power n minus r. Our a in this case is 2x, b is 3. So 6 combination 3 is 2x raised to power 3. Y, that was 6 minus 3. Our r is 3 times 3 raised to power 3. 3 raised to power 3 is 27. 2 raised to power 3 is 8. Then x cube and 6 combination 3. If you do the combination or you use binomial, Pascal triangle, you see that 6 combination 3 is 20. And so 20 times 8 times 27 gives us 4320 x cube. This is the 4th term of that expansion. Another similar question says find the coefficient of x squared in the expansion of x plus 2 over x all raised to power 5. So here, coefficient of x squared simply means by the time we group all the x part of this term, the index should sum up to 2. This is what we're saying. We have n is definitely 5, but we don't know what r is because we don't know the particular term where x squared is appearing. So we have to find r, and then we'll be able to get that coefficient of x squared. So tr plus 1, the r plus 1th term will be 5 because n is 5, combination r, x raised to power 5 minus r times 2 over x, which is our b raised to power r. That's from the formula. 5 combination r, we cannot do it because we need r to be a number. So we'll leave it that way till we get r, times 2 raised to power r, right, from here. 2 raised to power r, remember what I said earlier when we were doing 1 over b and something like that. Then this will also be x raised to power r at the denominator. X raised to power r at the denominator is the same thing as x raised to power minus r if we are to bring it up. That's why when we combine all the index numbers for x, we have 5 minus r, then minus r here as well. That's why we have this. For the r plus 1 term, we now have 5 combination r, 2 raised to power r, x raised to power 5 minus 2r, minus r is minus 2r, and so like we said, we have been able to group x to one portion of term, and so the index 5 minus 2r must sum up to 2. That's what we are saying on the particular term we are looking for. So 5 minus 2r must be 2. Then we're able to get r. Now r is 3 over 2. If r is 3 over 2, then we can put it back here for all the r, and we'll be able to get the coefficient. Since r is not an integer in this case, there is no term containing x squared. So we need r to be a positive integer, that is a positive counting number, a positive whole number, because we cannot do combination of a rational number. There's nothing like 5 combination 3 over 2. But let's say we got r to be a positive integer, then we'll be able to proceed from this point. So we conclude that there is no term containing x squared in our expansion. That's why we got this. Now, we have some exercises, and take note that general expansion for our binomial is given by this formula. We have the general term, which we just treated, the r plus 1 term. Every expansion will have n plus 1 term, that's binomial expansion. For negative or fractional powers or rational powers, this is the expansion, right? And in every binomial expansion, watch the pattern carefully. Coefficients follow Pascal's triangle. One power decreases while the other power increases, and the total power in each term remains constant. Thank you. You can go through the exercises, of course.